here. Okay, so we got everything under control. So it's great to be here. It's great to be in Santa Cruz. Spent a lot of time here, and these meetings are always great venues for discussing lots of current and future theoretical ideas. So I'd like to thank Steve and Charlotte for giving a nice introduction to lots of the material I'll go through in my talk. So actually, Charlotte went through a lot of the material in the beginning of my talk just to begin. So a lot of the questions we have about galaxies, understanding reionization, understanding galaxy buildup, really revolve around trying to have a very nice theoretical model to explain, for example, the evolution of the UV luminosity function, trying to understand how, say, basic buildup occurs from, say, redshift 10 to 4, understanding the evolution of, say, the galaxy stellar mass function, just for variety, I'll show another one than the song et al. One, but there's many, many people who have worked on this. And so basically you want a theoretical model to explain all this. So once you have a nice theoretical model to explain all this, then you essentially can start looking at whether galaxies can reionize the universe, whether you can understand galaxy buildup, whether you can match a lot of different properties. And so there's a very nice prescription for basically modeling a lot of observations. It's been found from a lot of work by Peter Baruzzi, et cetera, that you can basically start with a pretty simple stellar mass to halo mass relation. Basically, you have this nice relationship between these quantities where you have essentially AGN or other sort of feedback effects here, and maybe supernova feedback effects here. And if you implement a simple galaxy formation or efficiency prescription like this, and then you include the buildup of dark matter halos, you can essentially fit a lot of observables at low redshift, and it's found to work very well. And so the question is whether this could actually work at higher redshift. And so, as Charlotte said in her talk, basically they found from their very nice simple modeling efforts that they were able to basically use a very simple prescription, basically again build up dark matter halos, making these simple assumptions, something very similar to this, and then basically they were able to get a fit to the luminosity functions basically between redshift 5 and 7 all the way out to redshift 10. Basically explaining all the known observations and getting a good match. And so obviously that's very nice. However, when Charlotte put this together, she was effectively putting together this model in the face of some other observations which suggested that maybe these assumptions that she made about the efficiency of star formation in galaxies was not maybe such a great thing to do. There's this paper by Peter Baruzzi basically showing this relation basically between, say, redshift 4 and going to higher redshift. There was a paper based upon essentially cumulative number density matching the UV by Steve. There was essentially another more recent paper based upon some clustering analyses suggesting that basically there is actually evolution in this between redshift 4 and higher redshift. Here's a very nice plot from the Harakane paper, basically showing that the results in the stellar halo mass ratio, basically between redshift 4 and 7. Here is basically the redshift 0 result. Here are some theoretical models by some reputable, very good theorists, basically showing how this thing might expect to evolve in the models. And basically you get this very kind of non-monotonic evolution, and one might wonder whether all these results are actually real. And so what we tried to attempt to do is basically see whether we could come up with, we could do this in a different way and see if we came up with a different result. And so instead of essentially doing the cumulative number density matching and trying to assess the buildup of galaxies and looking at this evolution, instead of looking at essentially cumulative number density matching, say in the rest frame UV, in terms of rest frame UV luminosities, in terms of, say, galaxy stellar masses, we're just going to do this in terms of the rest frame optical light. So why would you want to use the rest frame optical light instead of using, say, stellar masses or UV luminosities? Well, the great thing about basically doing rest frame optical luminosity is that it's known to be a pretty good probe of the stellar mass. Once you go down to, say, 900 nanometers or 9,000 angstroms, you're basically getting down to the lower mass stars. It correlates pretty well with stellar mass. It could be more, when you actually have to worry about getting model fits to the data, it could be more model independent. if you actually just take the rest frame UV luminosity instead of an estimated stellar mass. You don't have to worry about dust correction so much. You also don't really have to worry about nebular emission lines. And so this is in principle a good way of going. By looking at 9,000 angstroms, we effectively avoid all the strong nebular emission lines that we see at high redshift. And so this is all work being done by Amaro Stefanon. Basically, the paper is coming along pretty well. Analysis is mostly complete. We're still worrying about a few corrections here or there in the analysis. So why is doing abundance matching in the rest frame optical better than in the rest frame UV? Basically, this shows you a plot of redshift 4 galaxies where we've essentially plotted where these things lie in the rest frame Z-band space, rest frame optical versus rest frame UV. This correlates pretty well with stellar mass. One thing you notice is that basically, if you look at the most massive galaxies, these galaxies are distributed over a wide range in UV luminosities, huge range, and you almost get this bimodality in this sort of relationship. Things correlate pretty well at lower masses, lower luminosities, and then they basically, it sort of bifurcates. So that's one reason to try to do this in the rest frame optical rather than the rest frame UV. What's another good reason to do? What's another good reason to do this in the rest frame optical rather than, say, using the stellar mass? And the stellar mass is obviously a very good thing to do if you can estimate it perfectly. However, trying to estimate it from the data can be kind of a dangerous prospect once you go to higher redshifts. This shows you the stellar mass estimates for a set of galaxies over the candles fields using stellar masses estimated using only one IRAC band versus using another IRAC band, just to show you that you can end up with huge amounts of scatter depending upon how you do the fits. And so basically, even using stellar mass can be a very dangerous thing and so in some ways it can be better just to do this using the rest frame optical luminosities, because essentially it's much more model independent. And again, the reason you want to, again, a big concern with just essentially trying to come up with estimated stellar masses is that when you get to these very high redshifts, you have these strong nebular emission lines. So this just shows you a stack of a bunch of redshift 6 galaxies from basic candles data, where we essentially stack both the bluer IRAC bands and the redder IRAC bands, and basically end up having this very strong O3 and H alpha light. And if you don't account for that or correct for that properly, you can end up getting the wrong stellar masses.
Richard?
Yes?
I know very little about AGB stars, but do those crazy AGB stars affect the Z-band?
It lasts, but it could. It's thought to be more important at the redder wavelengths. But I'm sure that, I'm not an expert on it, but I'm sure AGB stars can affect light at a lot of wavelengths. But it's mostly more at the redder wavelengths that it's thought to be a big problem. And so another thing is basically, and just to show you again the importance of the nebular emission lines, this shows you for a redshift 6 object. Basically, this shows you stellar mass versus UV luminosity. Basically, this shows you what you would get if you use 3.6 and 4.5. This shows you what you get when you use 5.8 and 8.0 if you do stacks. Anyway, basically the point is when you start to try to even estimate things like stellar mass, it can be a very difficult thing to do when you get to these very high redshift samples. So how can we do that? How can we construct a luminosity function in the rest frame optical? How can we get this? Well, now I'm going to explain to you how we can do this at very high redshifts. Okay, so first step is basically just select the galaxies. So construct large samples of galaxies just using LBG or photometric redshift selection techniques. So just first of all, just start with a large sample of objects that you've selected using huge amounts of data. Number two, basically just require a detection in the rest frame Z-band. So it's a pretty straightforward technique. Start with samples, and then basically require these things be detected in the rest frame optical. At redshift 4, this is pretty simple. You can just do it in the IRAC 4.5 micron band. At redshift 5 to 8, you can also, again, just do this with IRAC. However, as I'll show it, it's a little bit more challenging considering the data isn't nearly as sensitive. And so we throw away things which are really, really bright in the X-ray because they look like they tend to have power law spectra. Okay, so what do the data look like? So at redshift 4, you can just use the IRAC 4.5 micron data. This is essentially rest frame Z-band. Huge amounts of deep data. We have it both over the two goods fields and over ultravista. We also have, and here's the IRAC data that we have for the redshift 5 to 7 sample. From redshift 5 to 7 to get to the rest frame Z-band, we actually have to go to redder wavelengths, which means we have to go to the IRAC 5.8 and 8.0 micron data. A lot of people haven't really made use of this data so far because they've assumed it's effectively maybe worthless because it's not very sensitive. Well, it turns out that it is still pretty sensitive enough to detect some of the most massive galaxies, as I'm going to show you. And it's very nice because it allows you to do a very model-independent analysis. So here's the samples that we constructed from candles and goods. So basically at redshift 4, you can select large numbers of objects, almost 2,000. Redshift 5, 70. Redshift 6, 8. Redshift 7, 1. So again, as you go to higher redshifts, it becomes more difficult to find these objects. You can enhance the size of these samples, particularly at the bright end, by folding in all of Cosmos and basically all of Cosmos and UltraVista. And this shows you the samples you get if you do that. So we've added substantially the bright end, the high mass end, by folding in all of Cosmos. You might ask yourself, what do galaxies selected in this way look like? Here's a redshift 7 galaxy that we've selected in this way. As you can see, its SED looks fairly normal. Looks like a sort of a more massive galaxy. You might expect a more massive galaxy to look like at redshift 7. Okay, so what do we get in terms of the luminosity functions? And this is rest frame optical, not rest frame UV. We're pushing. So this is what you get, and we estimate this in the standard way. We basically take the selection volumes we estimate from our essentially searching for these things in the UV, and then we effectively account for essentially the depths in all the different IRAC bands and run a bunch of simulations to figure out the volumes. So this is what we come up with. That was from the first one was from candles and goods, and now this one's from including UltraVista. Now these are again rest frame optical. We can essentially we can actually come up with stellar mass functions from this. I'm not going to talk about this, but you can essentially convert this into a stellar mass function by calculating mass to light ratios. And this shows you the constraints that you can come up with redshift 4 to 7. I'm not going to talk about this. What I'm going to talk about is using this to look at the evolution of how the rest frame optical luminosity function compares with the halo mass function. So what we continue to do is take the redshift 4 luminosity functions, fit to some functional form, and then basically at an abundance of about 2 times 10 to the 10.5, match that to the halos, the halo mass function, and then look at how much evolution there is in the halo mass function at that density, and then try to use that to predict what you would find for galaxies. And so we've essentially shifted by the evolution in the halo mass function at this density, and this is what you come up with. We find that basically the evolution of the galaxy luminosity function in the rest frame optical seems to look fairly similar to what we find with the halo mass function. So then you can sit there and look at how the evolution of the halo mass, the galaxy stellar mass halo mass relation evolves, and just look at how this evolves with redshift. Here's some preliminary constraints. We're still refining this, worrying about Eddington bias and other things like this, which is important when you have to select things in the 5.8 and 8.0 data. And what we find is that there's basically very little evidence for evolution with redshift. And basically this seems to agree with the results of these theoretical models, which suggest very little evolution. Okay, so what are the uncertainties? Sometimes it's a little bit more challenging to select dusty or passive galaxies at redshift 5 to 8. So this could be a concern at redshift 5 to 8. It's also, you could worry about X-ray selected sources. So how does this compare with previous work? Steve had a paper which was based upon abundance matching UV, basically stellar masses based upon stellar population models, and basically photometric selection based upon, yes, okay. So how does this compare with this current work? This is what we get. This is what this other work gets. Pretty discrepant. But we think it's sort of useful to be able to do this in rest frame optical. Instead of using the basically the fits to these stellar masses, just use the rest frame optical light directly, and then essentially include fully passive and dusty galaxies at redshift 4 that we get from all of the ultravista filters we have over the cosmos field. And so basically, as you can see, there's a bimodality in this sort of relationship, so you can see the dangers of doing this in the UV. And so basically the point is if you do this, the other good thing about this is you also can match UV luminosity functions at high redshift. I'm not going to talk about this, but other natural predictions of this, and Charlotte discussed this, is if you start with a model like this, much like Charlotte's model, you can basically match a lot of current observations. You can basically match this tentative evidence for accelerated evolution. There's these are some new results at redshift 9 to 10 from Pascal-Oesch. Basically, that naturally reproduces this. This is basically what you expect due to you're accessing a steeper part of the mass function at redshift greater than 8 rather than redshift less than 8. There's a sort of debate in the literature, but it's effectively between these two types of models we won't talk about that anyway. But another thing about the models, it also perfectly reproduces the evolution of the Feynman slope with redshift. You basically can match all of this. So now let me just spend the last few minutes of my talk basically talking about the Feynman of the UV luminosity function. And Steve talked about this a lot. So the question is, how many UV continuum photons do galaxies produce? And you can just estimate this by calculating the UV luminosity function, and this is usually constructed by doing a wedding cake of surveys, constructing this luminosity function and integrating it up. And then the question is whether there's a huge contribution here. This question was supposed to be solved by the Hubble Frontier Fields program. So you take these powerful gravitational lenses, integrate very deeply, and repeat over 6 clusters, and then try to come up with results. And so some very small errors were claimed based upon the first year data. From basically the statistical errors were claimed. And so was the problem as solved as was claimed? So one major uncertainty is source size. And so source size is a significant uncertainty in all these analyses. If you don't get the source size right, you get the selection volumes totally wrong. And so this can have a big impact on the results. And so we went through a little exercise from the Hubble Frontier Field program based upon our own selections of these samples at redshift 6. And this shows you the luminosity functions at the bright end. This shows you the faint end. And depending upon what you assume about the size of the sources, we came up with very, very different faint end slopes, like by huge differences. I mean, these are just, and for the latter two cases, I could argue that these latter two cases are completely consistent with the data. I mean, in this new paper, this is a new paper that was on the archive last week, basically, both these things are in principle completely consistent with the data. I mean, if you allow for maximum uncertainties, and yet they come up with very different faint end slopes. So there's a major uncertainty in the results. And if you actually look at how this translates in the results, these are some of the results from Livermore et al. Based on, and if you just take a raw, simple fit to their raw data, you came up with a pretty steep faint end slope. This isn't the one they claimed, but it's basically a fit to their data without doing one of the corrections in the paper. And if you actually take our fit, where we assume smaller sizes, you come up with a very different result. And essentially, this is a major uncertainty in these analyses that needs to be incorporated properly in order for us to really understand what a lot of these things mean. Yes. Anyway, there can be large differences here. So another major uncertainty is basically the gravitational lens models. And how the question is you have these models, and the question is how magnified are the individual sources behind the clusters? And these are some extreme cases. The models are now better than this, but basically these are the regions where you have high magnification behind one of the clusters. So in principle, some of the early models differed by quite a lot. And so you can imagine if you apply the if you assume that a source is magnified when it's not, or you make some errors in this, it could result in large errors. And so we went through this effectively forward modeling approach, which I don't have time to explain, but basically using MCMC and iterating over all the parameters, but you can basically derive confidence intervals on the shape of the luminosity function based upon assumed errors in the models. And here's sort of the most optimistic case, 68-95% confidence intervals. Here's one of the worst cases, and basically you can end up with huge errors where you can basically end up with turnover. So there's been statements made about how there's no turnover to minus 12 or minus 13. Well, if you essentially fully include the uncertainties of these models, in some of the worst cases, basically you can get a turnover at minus 14 or minus 15. Anyway, it basically happens due to the fact that you end up with scatter in the models. And basically scatter in the models basically drives you to a Feynman slope of minus 2. And basically, it allows you to basically scatter sources that are actually minus 15 all the way down to minus 13 or so. And so you can end up, so anyway, there's a variety of cases you can assume. Any case, the basic point I want to say is, so there's been statements made about how the frontier fields data provides strong evidence against the flattening of the UV luminosity function at minus 14. However, if you look at our constraints that we come up with from the lensing models, you can see that essentially there's no problem in fitting a lot of theoretical results. Yes, I'm basically done. There's no problem in actually fitting. The current observations are fully consistent with a turnover or a flattening of the luminosity function at minus 14. And so I would say that the frontier fields data are perfectly consistent with a flattening of the luminosity function at minus 14. And again, a point I'd like to highlight is systematics are a major concern for the Feynman and the luminosity function. Here's the luminosity function at redshift 2. From the UDF, the Feynman slope is claimed to be minus 1.35 with error bars, really small error bars. And then from basic lensing analysis, the Feynman slope is claimed to be minus 1.72 with very small error bars. They differ at 10 sigma. So systematics are a major concern. So just to summarize, basically, by looking at the rest frame optical luminosities of galaxies, by effectively folding in the red or IRAC data, we've essentially come up with some constraints which suggest fairly minimal evolution in the galaxy stellar mass to halo mass relation between redshift 4 and 7. We've also, another thing that I discussed in this talk is basically the prevalence of ultra-faint galaxies. And I'm not trying to leave the impression that we understand the prevalence of ultra-faint galaxies. I'm just trying to, what I was trying to point out in my talk is that we have some major uncertainties here regarding galaxy sizes and also in incorporating some of the uncertainties from the gravitational lensing models into actually essentially coming with uncertainties or confidence intervals which include all the errors in our analysis. And so we're still working on this. So that's all I have to say. Thanks. Yes, Eric. I don't know who the chair is here.
Maybe I missed it, but do you have an interpretation of the difference that you find for the stellar mass to halo mass evolution? So what about optical rest frame luminosities versus UV luminosities that would cause such discrepancy? Do you have idea?
Well, I mean, one of the concerns is basically including the passive or dusty galaxies. So if you do the abundance matching in the UV, then it turns out that you may not fully include the contribution. You may essentially get to a certain, essentially you want to make sure you add up all the massive galaxies before you start to hit essentially the lower mass galaxies. And if you do things in, yeah, I mean, it's a little bit complicated, and it would require a bit of discussion, but I mean, the concern is that you want to make sure you add up all of these objects. I mean, if you do the ordering this way rather than this way, you want to essentially make sure you include all of these objects before you start including these objects. And if you do it this way, then you could essentially be essentially scrambling the ordering. I mean, it's a little bit difficult to discuss this in detail, but yeah, I mean, we should probably talk about this afterwards. But I mean, it seems obvious to me that you would want to essentially order this strictly, basically in terms of the rest frame optical or stellar mass rather than doing it this way. Because if you do it this way, essentially you're introducing a huge amount of scatter, into your relationship, which may wash out the trends that you'd want to pick up. It's also possible that some of one of the problems with all these previous analyses is it's very difficult to remove all systematics. So we could discuss this as well. I mean, one of the problems with, for example, the
Richard, that's good.
yeah,
Eric?
sorry.
Okay, I have two questions. I think both of them quick. One, so my understanding is the evidence for the changing halo mass stellar mass relations from clustering. What does that evidence actually look like? Is it weaker clustering? Or stronger clustering?
Some redshifts are stronger and some redshifts are weaker. And so if you actually look at the
high redshift, does it get weaker?
I can just quickly show you their result. This is their result. It's easiest to see on this plot.
Well, that's
So basically at redshift 4, you essentially have I have to think about this quickly, but basically you have one extrema at redshift 4, and then you have the other extrema. At redshift 5 and 6, they're consistent with no evolution. Redshift 7, it's at one extrema, and redshift 4, it's the other extrema. The concern I have with all these analyses, and I don't mean to throw mud at these people, is that basically if you don't estimate your redshift distribution properly or anything like that, then you essentially apply the Limber relation, or you apply it, and you essentially assume it's more washed out or less washed out than it really is, and then you end up getting the wrong answer. And I'm not trying to say, but I think it's a very hard thing to do this right, and I think that there's a lot of work to be done.
All right, let's thank Richard again.
Sorry.
Some